We study the few-shot physically aware articulated mesh generation problem. Physically aware articulated meshes play a crucial role in various downstream tasks, helping an intelligent agent to learn segmenting, tracking, manipulating articulated objects in a simulation environment. Despite their promising application scenarios, existing articulated mesh datasets are only at a small scale, usually containing no more than 100 instances for each category. This naturally points us to devise a generative model that can generate articulated meshes with diverse geometry, high visual fidelity, and also correct physics to support physically realistic simulation. Solving this task poses two main challenges, namely few-shot generation and physically aware articulated mesh generation. Existing mesh generation techniques either cannot generate diverse meshes from a few examples or cannot model correct object-level constraints imposed by the functionality of their generated objects. Our work designs a hierarchical mesh deformation-based generative model that tackles the aforementioned challenges using two key innovations, namely hierarchical mesh deformation and a physics-aware correction scheme. We propose an object-convex hierarchy. Then the hierarchical mesh deformation is realized by learning a convex-level deformation-based generative model, and further with a mesh deformation synchronization strategy, to compose individual convex deformation spaces together to object-level spaces. When learning the convex-level deformation model, we propose to transfer cross-category shared deformation patterns from large-scale rigid mesh datasets to the target articulated mesh dataset. We represent convex deformations via cages, and record common deformation modes via deformation bases. We train a neural network to parameterize deformation bases. By pre-training it on rigid meshes, and fine-tuning it on the target dataset, we can transfer shared deformation patterns to the category of interest for deformation space enrichment. Given individual convex deformation spaces, instead of composing them together directly, we further propose a convex deformation synchronization strategy to capture object-level shape priors such as symmetric part geometry. We estimate a set of synchronization transformation matrices, such that we can replace convex-level deformation parameters with a single object-level deformation parameter. We then use a mixture of Gaussian to model the distribution of object-level deformation parameters. We can sample object-level meshes by varying object-level deformation parameters. Further, we design a physics-aware deformation correction scheme to encourage the generative model to produce physically realistic deformations and to improve the physical validity of synthesized meshes. It is composed of a penetration depth-based penalty term, measuring self-penetrations to provide physical supervision for the network, and a collision response-based shape optimization strategy to mitigate self-penetrations. Next, we present our experimental results. For quantitative evaluation, our method can outperform baseline generative models by a large margin, on both metrics measuring generative ability and physical validity. We can generate a diverse asset of physically aware articulated meshes by only observing a limited number of examples. Moreover, our method can also be applied to rigid object categories for few-shot mesh generation. We also conduct a series of ablation studies by validating the role of some crucial designs in our method, including hierarchical mesh deformation, transfer learning for the convex-level deformation model, physics-aware deformation correction scheme, and test time adaptation. Each of them plays one of our core contributions. Thanks for watching.